Okay, so we're very happy to have with us today Ariel Kulik, and he's going to talk about recurrences and applications to algorithms. So this is an algorithm talk.
So thank you, Yuval. It's a young work with us. So what we're going to have is a fairly long introduction. It will present the main algorithmic idea of this paper, along with the mathematical problem we needed to solve in order to analyze the algorithms. And we will then present the main results. Then, depending on the time and the preferences of the audience, we will either speak about how to attain the result for recurrences, or we will we will show how to improve the algorithmic result seen in the introduction. And we're going to have a short summary. And if at any time you have questions, something is not clear, please say something, stop me. I have no feedback. I only see my own screen. So please assist me with that. So we're going to speak about vertex cover through this talk. So I want to make sure we all know what vertex cover is. So given an undirected graph G, we say that a subset of vertices is a cover or a vertex cover if for every edge UV in the graph, it has a non-empty intersection with the edge, with the endpoints of the edge UV. So we have this small graph here, and those two vertices form a cover. And you can cast vertex cover as a decision problem, in which given the graph G and some number K, we want to decide whether G has a cover S with at most K vertices. And it also can be cast as an optimization problem. We want to find a cover S of G such that the number of vertices in S is minimal. And we will play with this definition through these tokens. This is one of the reasons I want to discuss them. And the problem is NP-hard. And from the point of view of approximation, it is pretty much well understood. So we have a polynomial time to approximation for the problem, which given a graph G, which has a cover of size K, always finds a cover S with up to 2K vertices. And there is no 2 minus epsilon approximation under the unique case conjecture. So as far as approximation go, we pretty much understand the problem well. And what we're going to do is to play between approximation algorithms and parameterized algorithms. So I will define what is FPT, fixed parameter tractable algorithm. So, and then we will present the definition of parameterized approximation. So the idea in parameterization is that we associate a parameter with every input instance. So if we want to, so given a language L, we define its parameter to be kappa of the instance, which is some number. And what we want in parameterized algorithm is to decide whether the input instance is in the language L, and we want to run in time to be some function of the parameter times a polynomial factor. And we will often use this O star notation to ignore the polynomial factor. And where here n is the size of the input and k is simply the parameter of the instance. And this is a special class of non-polynomial time algorithms. And vertex cover can be cast as a parameterized problem. So as I already said, in the decision version, the input is G and K, and we want to decide whether G has a cover S with up to K vertices. And it's not one of the ways to define a parameter for this problem is to have the parameter to be K. It's often referred as the standard parameterization of vertex cover. It's not the only parameterization. Of course, you can think about other things like properties of the graph G and so on. And often those other parameterization makes more sense, actually. But this is the standard way the problem is studied. And as far as the parameterized algorithms go, the best parameterized algorithm for the problem has a running time of 1.273 to the power of k. And there was a significant effort to reduce the base of the exponent in this algorithm. And it's also known that there is no sub-exponential time algorithm for the problem under ETH. And what we're going to discuss is an high.
Yeah, do we know, like, is there some concrete lower bound under SETH?
Can you repeat? I couldn't hear you well.
Yeah, so here you're saying that under ETH, then you need exponential time in terms of K. So one might expect that maybe given SETH, then you can get a specific lower bound. Like
I also expect that, but no one knows how to do that. No, it's an open problem. There is no lower bound I'm aware of for the base of the exponent. And I think it's one of the reasons that this race to reduce the exponent has stopped, because you don't know where to go, and the algorithms became more and more complicated. So they were not interesting in some sense. They did not provide some in-depth understanding. So, and you didn't have any lower bound to reach. So my guess is that if someone will be able to provide some lower bound, then immediately people will start work again on improving the algorithm. And I'm not aware, and as far as I know, there is no lower bound.
Ariel, just another quick question. How bad are the constants? Like when you get these asymptotic improvements?
They're wonderful. They're wonderful. So first of all, there is a problem because it's very hard to understand what are the constant, because if I just replace this 3 with 4, then the constant is 1 from some point on. So you need to understand. So you need to properly frame the question. But the issue is that one of the techniques in parameterized complexity is kernelization. That is, we can reduce the instance of the problem using a pre-processing algorithm. And specifically, vertex solver has a very efficient kernelization. So the first thing you do, it won't affect the asymptotics of the running time, but it will make sure your instance, when you start with it, it's already very small. So it doesn't seem that the coefficient here is significant. The algorithm is very technical, but it's not complicated algorithm. Usually the algorithms are simple branching algorithms for this problem. But I will be surprised if the constant is, so again, it's a problem of framing because the constant is definitely 1. But I think but I think that if you will run this in practice, you will see that the running time pretty much match it with small coefficient. At least if you will replace the 1, 2 by 1, 2, 8, then you will get it from pretty much the start.
I see. Okay, cool.
It shouldn't be high. I'm not sure whether the algorithm was ever implemented, this specific algorithm. I don't know.
And are there any heuristics that can be conjectured to do better, or you believe that this is indeed the best known algorithm?
I think that if you run this algorithm in practice, it is much faster than what you see. Because it's a branching algorithm, and the analysis is based on the worst case. And it's often conjectured that we don't know how to analyze these algorithms well. So we cannot, there's no way to capture long-term dependencies in branching algorithms. So it's likely that the algorithms are in fact faster, but I never tried to implement them. I never tried to study them from a practical perspective. So I'm not sure. I assure you that the algorithms I'm going to show you today are simple to implement and they're practical in some sense.
And finally, any relations between this and other parameterized NP-complete problems? Like, I know, so there's been a lot of, so Yuval Filmus already mentioned the SAT conjectures, but maybe other NP-complete problems that are related to this?
So in what sense? I mean,
in the sense that the breakthrough on some other problem that is not clearly identical, isomorphic to vertex cover, will lead to progress on vertex cover or vice versa?
Not that I'm aware of. Not, again, the playground here is the coefficient. So
yeah. No, but Yuval Filmus, the reason he asked was that there are
yeah.
some instances where you can get,
Yes.
fine-grained complexity really is about that. So the question is whether if you replace SAT by some other NP-complete problem, you can get such a
It's not what I'm like. It's not something I'm very familiar with, but last time I asked this question to people who are familiar with the specific issue, the answer was no.
Okay.
It's still unknown. There's no good technique to low bound the constant of vertex cover. I think it's a very good question, but I don't know how to tackle it.
Okay, thanks.
Okay. Thank you for asking. It's very nice to have feedback and people speak with me. So what we're going to discuss is parameterized approximation. So we will take a hybrid between the approximation algorithm and the parameterized algorithm. So we will take some alpha, and we will define it to vertex cover specifically. You can find general definitions for arbitrary problems, but the talk will focus on vertex cover, so we will only define the parameterized approximation for the specific problem. And for some alpha, we say that an algorithm is a parameterized alpha approximation for vertex cover. If given a graph G which has a cover of size k, the algorithm returns a vertex cover of size alpha k or less. We will also allow it to actually return a vertex cover of size alpha k or less with constant probability because our algorithms are going to be random. And we want the running time to be in FPT, to be fixed parameter tractable. And of course, just FPT doesn't make any sense here because we know that vertex cover is in FPT. And what we really want is a trade-off. We want to show that as we allow higher approximation ratio, we relax the requirement for optimality, we want to reduce the running time. And vertex cover has been studied from this perspective. And previous works, one of the previous works provided a complete trade-off between the exact parameterized algorithm to polynomial time to approximation, and specifically those obtained alpha approximation in time, which is 1.2378 to the power of 2 minus alpha, all of this to the power of k. And you can see here in the graph the base of the exponent of this algorithm as a function of the approximation ratio. And this result, one of the ways to obtain it is by an approximate pre-processing. And other work by Kulik and Fernau designed dedicated branching algorithms, which were designed to provide an approximate solution. And those provided results for specific approximation ratio. And for example, for 1.0883 to the power of k, sorry, for 1.5 approximation, the running time was 1.0883 to the power of k. And it's important to say that it's not clear whether you can get, for example, a 1.5 approximation in time which is sub-exponential, but even getting anything smaller than 2 approximation in time which is sub-exponential is a major open problem. So it makes some sense to try to reduce this exponent. So I don't have a very good lower bound for to claim that there is no sub-exponential running time algorithm for the problem. Though for when alpha is close to 1, there are some lower bounds. And so we have this graph, and essentially the result we have in the paper is this red line. That is, we get a significant improvement over the trade-off between the running time and the approximation ratio. And okay, so we're going to discuss some basic algorithms and start to play with them to see the main algorithmic idea. And we will start with one of the most simple algorithms for simple parameterized algorithm for vertex cover. And it goes as follows. We get an instance of the problem, G and K. If K is negative, we know we can return false. If there are no edges in the graph, we can return true because we know the graph has a vertex cover of size K because K is non-negative. And otherwise, there is some edge in the graph, UV, and we solve the problem recursively with G minus U and the parameter K minus 1 and G minus V and the parameter K minus 1. And the idea is that in any optimal cover, either U is in the cover. Okay, so let's say the graph has a vertex cover of size K, So either U is in this vertex cover or V is in this vertex cover by the definition of the cover. And let's assume for simplicity that the vertex U is in this cover. So in this case, it holds that the cover without U is a vertex cover of G without U of size k minus 1. So this will return true. And you can also show that the other direction, that if one of those is true, indeed the graph G has a vertex cover of size k. And we call this operation in some sense branching, because we branch over the two options that U is in the cover, in the optimal cover, or V is in the optimal cover. And the running time of this algorithm is 2 to the power of k, and you can take a look at it as a branching tree that each node here in the branching tree represents a recursive call. And what happens is that the depth of this tree is k, here in the example is 2. And the algorithm can be viewed as if we go over the leaves of the tree and we look for some special leaf which represent cover. And what we're going to do is to try to play with this algorithm to obtain an approximation. So what we'll do, we will repeat this process of branching over the options that the vertex U is in the cover and V is in the cover for k plus 1 times instead of k times. So if we look at the branching tree, we will double the number of leaves because we added a layer. But if we try to figure out how many leaves now represent a cover, then the answer is at least k plus 2. And the reason for that is that every time we do this branching, one of the options reduces the minimal vertex cover size by at least 1, or by exactly 1. But at least one of the options reduces the minimal vertex cover size. And as long as we reduced it for k times, we will end up with a cover of size k plus 1. And you can play with the combinatorics of this, and you will figure out that you will have k plus 2 good leaves. So we have them here drawn. So the basic idea is that while we increase the search space, we also increase the number of leaves that represent a solution, but the number of good leaves grew much faster than the number of leaves. So of course now it doesn't make sense to go over the leaves as before, but here randomization can come into play. So instead of branching over the two options, we can choose one of them at random. That is, our algorithm can be as follows. We will pick an edge UV in the graph, and with probability half, we will add U, one of its endpoints, to the cover. And with probability half, we will add the other endpoint to the cover. And we will repeat this process for alpha k times. That is, we will look for a solution which is of size alpha k. Now, this is a polynomial time algorithm. It doesn't do any actual branching. And so the real question now is, what is the probability that this algorithm finds a cover? And actually, for this algorithm, it can be understood pretty easily. It can be calculated fairly easily. And the idea is that we can have a set of indicators, xn, such that xn equals to 1 if at the nth step of the algorithm, the vertex we choose reduced the minimal vertex cover size. And otherwise, we set it to be 0. And because there's always one good option, we have that the probability of xn to be 1 is at least half, even if we condition it on previous events. Therefore, the probability that we found a cover is the probability that we reduce the minimal vertex cover size at least k times, because we assume the graph has a vertex cover of size k. And this in turn can be lower bounded by the probability that the binomial random variable with alpha k trials and probability half is at least k. And the reason we can derive this lower bound is this probability of half of xn to be 1.
Okay, so here if you choose alpha equals 1, then you get the original 2 to the k algorithm. And if you choose alpha equals to 2, then you essentially get the another algorithm you randomized for two approximation. So is this known? Is this useful anywhere if you want to sample vertex cover of size 2k?
I'm not aware of uses of this for other application. first of all, you're right. If you choose alpha to be 1, you get exactly the success probability is 2 to the power of minus k. If you want it to be 2, you get actually your success probability is some 1 over polynomial, or at least 1 over polynomial. Maybe you can find a tighter lower bound for it. No, it should be half at least. But I don't know any other applications. No. Okay, but we converted our problem into some standard question in probability. So this question has an answer in the sense that the probability of a binomial random variable with alpha k trial, the probability have to be at least k, is at least 1 over alpha k plus 1 squared times the exponent of alpha and the divergence of 1 over alpha and half, and all of this to the power of minus k. And we can replace this exponent expression by C alpha just to make it look nicer. And here, D is the Kulik-Leibler divergence. And this is a standard tailbound for binomial distributions. And one of the ways to derive it is using the method of times, which will play a major role in the main mathematical result of the paper.
Yeah, but when you usually prove the Chernoff bound, you don't use the method of types. You just compute the exponential derivative function and apply Markov or something.
Yuval, I can, I couldn't hear you well. If you can repeat.
Yeah, I'm saying the usual proof of the Chernoff bound is not through the method of types.
Yes, so I don't know how to. When I first found this lower bound, many people referred me to Chernoff, often lower bounds and so on. But it's not trivial to derive this bound using Chernoff. I still don't know how to do that, but it's very easy to do so using the method of types. So maybe you can derive it using Chernoff, but it's not the easy way to do that. And for sure, I was able to scale the method of types for other results, and I didn't know how to do that with Chernoff. Okay, but given this lower bound, we can think about an algorithm. And the algorithm will be as follows. We will run this randomized branching algorithm for the inverse of its success probability for alpha k plus 1 squared times C alpha to the power of k. So what we will have is that if the graph has a cover of size g, we will now have constant success probability of finding a cover of size alpha k. And the running time of this algorithm will be some polynomial times C alpha to the power of k. So the base of the exponent will be this C alpha. And what we want to do is simply to draw it. So here in the yellow to orange line, we have this C alpha as the function of alpha, the approximation ratio. And what we can see is that, again, for, as you mentioned, when the alpha equals to 1, it's essentially 2. So we get a 2 to the power of k algorithm if we want to have an exact solution. When alpha is 2, the value is 0, so we get a polynomial to approximation up to the randomization. For example, however, for 1.5, we get running time, which is 1.0887 to the power of k. And it only differs from the previous best result in this 7. Previous best result for 1.5 approximation was 1.0883 to the power of k. So what we get—
the success probability here is constant. I forgot this.
Yes, the success probability is constant. In that sense, it's a drawback of the algorithm. It is a randomized algorithm versus the deterministic algorithm of the previous results. But what we see is that we took a very naive algorithm for vertex cover. We used this idea of replacing branching with randomized branching, and we got a very nice results for parameterized approximation. So the next steps that make sense is to try to take some slightly less naive algorithm for vertex cover and do the same. So we will take now some slightly more sophisticated algorithm. It has a running time of 1.46 to the power of k. And it goes as follows. If there is a vertex v in the graph with degree at least 3, we branch over 2 options. That is, either v is in an optimal cover, or if v is not in an optimal cover, it holds that its neighbors are in an optimal cover, so we branch over those two options, that either V is in the cover or the neighbors of V are in the cover. Otherwise, the maximum degree in the graph is at most 2, and those graphs consist of circles and lines, and you can find a minimum vertex cover for them in polynomial time. And you can lower bound the number of leaves in the branching tree of this algorithm by the recurrence P of k equals to P of k minus 1 plus P of k minus 3, and you will get this running time. So it's still a very simple algorithm, but it is significantly faster than the previous algorithm. And we can now think about a randomized version of this algorithm. So we'll need to fix some gamma between 0 and 1. And what we'll do is that we'll apply the same algorithm, but we replace the branching with randomized branching. That is, if there is a vertex V of degree at least 3, then with probability gamma, we will add the vertex to the cover. And with probability 1 minus gamma, we will add 3 of its neighbors to the cover. Otherwise, the maximal degree is at most 2, and we can find a minimum vertex cover in polynomial time. So if you look at this algorithm, it is a polynomial time algorithm. Again, it doesn't do any branching. And it always returns a cover. At some point, the maximal degree in the graph will be minus 2, and we will find a cover. And the only question is, what is the probability that the algorithm returns cover of size alpha k? That's the success probability we're looking for. So we can have this capital P of B and K to be the minimal probability that the algorithm returns a cover of size B. B will be our budget. Given that the graph has a cover of size K, K here will be our parameter. And what we can have is that write this very large recurrence. We'll get back to it in a second. And it can be shown that this capital P of B and K can be lower bounded by this recurrence. So let's take a look at it. So we have here P of B and K equals to the minimum over 2 expressions, and with some initial conditions. And what is the first expression? The first expression deals with the case in which the vertex V is indeed in an optimal cover. So in this case, with probability gamma, the algorithm adds it to the cover. So our budget reduces by 1 because we added the vertex to the cover. And also the minimal vertex cover size reduces by 1. And with probability 1 minus gamma, it holds that we add 3 of the neighbors of V to the cover. And so in this case, we reduce the budget by 3. But because V is in an optimal cover, it may be that we did not reduce the minimal vertex cover size at all. So the parameter stays the same. And the second expression will deal with the case that the vertex V is not in an optimal cover. So the same logic applies here. With probability gamma, the algorithm adds V to the cover. So in this case, the budget decreases by 1, but the vertex is not in an optimal cover, so the parameter stays the same. And with probability 1 minus gamma, the algorithm adds the neighbors of V to the cover, or 3 of them. They're all in an optimal cover because V is not. Therefore, the budget decreases by 3, and also the parameter decreases by 3. And we also have the initial condition, that is, if the budget is negative, we cannot find any vertex cover of negative size. And if the budget is non-negative and parameter is 0, that is, the graph has a cover of size 0, then the algorithm will surely find a cover of size 0 within the budget because the graph has no edges. And this is an intuition. It's not a formal proof, but it's fairly easy to construct a formal proof based on these claims. And so once we have this in place, we can think about the following. So this P of B and K can be computed using dynamic programming. If you give me the values of B and K, I can compute the value of this function P. So we can run our randomized branching algorithm for 1 over P of alpha k and k times. So we will have a constant success probability to find an alpha approximate solution. So this is a way to derive an alpha approximation algorithm for any alpha. And it's surely an alpha approximation algorithm. The issue is that we don't know its running time, because its running time is something polynomial times 1 over P of alpha k and k. So conceptually, we want to find some constants C such that P of alpha k and k is roughly c to the power of minus k. And this can be formally stated as the limit of 1 over k log P of alpha k and k. We want to evaluate this limit, at least if we assume that the behavior is exponential. And with some surprise,
Is a constant?
What did you say?
Do you think of gamma as a constant?
I assume that gamma is a constant, yes. Yes, I assume in some sense, let's say, yes. I will then, on later stage, I will show how we can find the optimal gamma, but I assume the gamma is constant throughout the execution of the algorithm. So
it could be that the optimal value of gamma depends on being k.
It makes sense to do that. I don't know how to do this efficiently, but it makes some sense to do it. Often the algorithm does not know k during its execution, so it's not something trivial to implement, but I assume that gamma is fixed.
But you can enumerate over k, so you can let the algorithm know about k. That's not an issue. Using dynamic programming, you can probably find the optimal gamma.
Can you repeat that?
Yeah, I'm saying the algorithm can guess k because there are only n options. So you can assume it knows k, and then you can find gamma using dynamic programming also.
I will think about it later. I don't see it, when you speak about it, I don't see how to do that. But maybe it's possible we can talk about it later. So our problem became that in order to understand the running time, we want to understand this recurrence. And with some surprise, I didn't find a solution for the recurrence. And I'm still surprised there was no solution for the recurrence. And at this point, the focus of my work shifted from algorithms to just solving the recurrence. Okay.
Ariel, can I ask a question?
Sure.
Does it make sense to adjust these probabilities, the gamma, or even the 0.5 for the two branching thing as I go along? So sort of have some estimate of what happens in your subtree?
I think that yes. I don't know how to do that, but I think that yes. The issue is that intuitively I'm with you. There are some reasons to believe it will not get any improvement. But in some sense, what happens is that I needed to start with a simple thing before I get to the next step of making it more complicated. But it seems interesting to try to play with the gamma as you progress, and maybe you can use this to reduce the running time from exponential to sub-exponential or something like this. It makes it, I have the same intuition as you have. I just don't know how to apply it to the problem. And one of the problems is that if at the moment solving the recurrence is complicated, if you make the gamma dynamic, it will render it even more complicated. So
yeah, that makes sense. Thanks.
So it's only a question of having it step by step. And regarding the initial algorithm, which has probability half, it actually there you can justify the half because the cases are symmetric. So it really doesn't make sense to say that the vertex V should have a higher probability than V. And it doesn't make sense. But for those cases, you can think, actually, before you will go for such options as making the gamma dynamic, I will try, or maybe it's something you can do along the way. You can always run an approximation algorithm at every step of the branching out of the randomized branching algorithm, and then try to deduce some information from, for example, from the approximation algorithm about the current state of B and K, and then of at least K of the parameters, and to adjust accordingly. Maybe you can do that.
Right, and having gamma depend on B is no problem because B you do know.
You do know B, but I don't think it makes sense to make gamma depends only on B. Because it's predictable. You don't get any information about the specific instance you have at the end. So I don't have a good intuition for that, but if you want it to depend on the parameter, it makes a lot of sense. You don't know the parameter. That's the issue. Okay, so what are the main results in the paper? The main result actually is to generalize the recurrence we just seen and to find a solution for that. Not for this specific one, for a wider family of recurrences. And then what we have is parameterized approximations for vertex cover and street set, and they're based on the idea of using randomized branching and using this solution for recurrences to both get the running time and both have some good intuition about how to design these algorithms. And the algorithms are simple and they provide significant improvement over the running times of previous algorithms. Let's discuss about how to generalize this specific recurrence into a family of recurrences. So we have here that P of B and K equals to minimum of two expressions, and each expression is some coefficient times P of B minus some number and K minus some number plus another coefficient times P of B minus some number and K minus some number. This time the number is 0. And we can write our recurrences in this way. It will be the minimum of coefficient times P of B minus number and K minus number. So this is a more general way to write them. The next thing we can think about is that now each of these expressions, we will call them terms, is the sum over two smaller expressions. And we can change this 2 to be an arbitrary number. So that is, we will have the minimum over the sum of I goes from 1 to R1, the gamma 1i, the ith coefficients, times P of B minus B1i, the ith budget reduction, and K minus K1i, the kth parameter reduction. And we can do the same for the second term. And the last thing we want to do is to also generalize the number of terms. Here we have two terms. We can say that we have some n terms, and we'll take the minimum over those n terms, and each term will be the sum of coefficient times P of B minus number and K minus number, as before. So
Ariel, are you insisting on convex combinations?
I cannot hear you well, so if you can repeat.
I want to ask if you insist on convex combinations or they can be general coefficients.
I want more than, I think that convex are coefficients that sum into 1, right?
Yeah, so probability distribution.
I want them to be probability distributions, yes. You know, I needed to focus on something, so this is what I needed to solve. So I solved that. It's likely that you can. It's likely that you can generalize that, but if you want to do that, you need to start with a good problem that it will assist in solving. And I don't have application for the cases in which the gammas do not sum into 1. So what we have so we considered functions P, which satisfies the recurrence we just seen, with the same initial conditions as before. That is, P of B and K equals to 0 for negative B, and P of B and 0 is 1 for non-negative B. We have some requirements. We need that the number of terms will be a natural number. For every term j, we want its length rj to be a number. As Ron mentioned, we want the vectors gamma j to be a distribution. We also want it to be a distribution with positive coefficients. It simply doesn't make any sense to have a coefficient of 0 here. You can just remove it. And we want the kj's to be natural numbers and the bj's to be positive natural numbers. And we will refer to this tuple of gamma j, bj, and kj as the term. And those are the elements, the variables, which define the term sum of I goes from 1 to rj, gamma ji times p of b minus bji and k minus kji. So those are the recurrences we want to solve. There's an asterisk here because we have some additional condition, which is very technical and it deals with some corner cases, and you can find it in the paper. But for the purposes of this talk, those are the recurrences we solve. And the main theorem goes as follows. For every alpha greater than 0, we define an alpha branching number. That is gamma j. We define the alpha branching number of the term gamma j, bj, kj. And we denote it by mj, and it is a function f of the alpha and gamma j, bj, kj. And I'm not going to write f here, but f is defined using a quasi-convex minimization problem. So it's not closed form, it's defined using a problem, but this problem is nice enough so we can solve it for any practical application. And the main theorem states as follows. It says that the limit of 1 over k log p of alpha k and k is minus the maximum alpha branching numbers of the terms. Or this can be equivalently stated without the mathematical rigor that p of alpha k and k is roughly the exponent of the maximal alpha branching number to the power of minus k. And it has two implications. The first is that we have a solution for the recurrences. We have the number, we have their asymptotics. But we also have a structure. We know that the recurrence is dominated by a single term which has the maximal branching number. So it's not only the solution, it's something insightful that can be used to design algorithms. And the first thing we can do is take an example of how the theorem can be used. So we have this recurrence before, and we didn't know, it's the same one we saw in the introduction, we've seen. And I can tell you, because I know, that gamma equals to 0.74363 is a good number, believe me. And by the theorem, what we have is that the limit of k goes to infinity, 1 over k log p of 1.5 k and k is minus the maximum over the branching number of the first term and the branching number of the second term. I can plug the optimization problems that solves this f into my computer, and I will get a number. This is roughly minus 0.0427, a number. And it can be also written as p of 1.5 k and k is roughly 1.04664 to the power of minus k. But as you recall, we already seen a 1.5 approximation algorithm for vertex cover with running time, which is 1 over this p of 1.5 k and k. But we just didn't know what this value is. But now we get an answer. That is, the value is 1.0436 for, maybe I lost some digits when I said that, to the power of k. So this simple algorithm, by now, actually significantly improves the state-of-art result. And you can ask, where did I get this gamma? And the answer is that the problem of finding the gamma for which the maximal branching number is minimal is also quasi-convex. So I can just plug it into my computer and get an answer. And actually, for the specific recurrences we're handling here, there something you can write some new closed form formula for the branching number, for the branching numbers. And the result in the paper are simply applications of these ideas of randomized branching along with the solution for the recurrences. And for example, for approximation of 1.5, we get running time of 1.017 to the power of k. And the algorithm is basically a variant of the algorithm with the three we've just seen. It's a simple algorithm. For smaller values of alpha, we took a variant of the textbook algorithm, and we obtained, for example, for 1.1 approximation, running time of 1.6 to the power of k. And it's also harder to compare. What's nice in 1.5 approximation is that I have something to compare it with. If I want to use faster algorithms, faster exact algorithm for vertex cover, the issue there is that they have complex recurrences, which I can still not solve. But those are the main algorithmic results in the paper. We also have results for 3D set, which I'm not going to discuss. And I need to discuss the related works about recurrences. And here it was a bit surprising because recurrences in single variables are pretty much well understood. They're taught in, I think, combinatorics for first-year students. And once you go beyond that, we know fairly little. The only similar work we found is a work by Epstein from 2006. It also considers a class of multivariant recurrences, but those are simply different recurrences. And the work is commonly used in measure and control algorithms within exact computation, also in in parameterized complexity. So I need you to vote. We can now go to one of two options. We can discuss a bit how to attain the recurrences. It will be a bit a heavy mathematical topic. And the other option is to discuss discuss how to improve the algorithm. So I need someone to give me feedback about what you want.
I vote for algorithm.
You vote for algorithms. Okay, so you want. It's much nicer to have the algorithms than the heavy mathematics, I assure you. I think just I want to mention one thing about the recurrences. We use the method of types. We use tools from information theory, and I wasn't aware of other applications of information theory or the method of types in computing. If someone is familiar with one, I will be happy to get a reference to it. So what we're going to do now is to discuss how to improve the algorithm we've just seen. So we have this algorithm. It works in, as we just mentioned, it has the runtime of 1.0.437 to the power of k. And it works by finding a vertex v of degree at least 3 and adding it to the cover with probability gamma. And with probability 1 minus gamma, we select 3 of its neighbors. And we've seen that we can lower bound its success probability using this recurrence. And what we're going to do is to use some more refined analysis. And we will focus on the case that the vertex v is in a minimal vertex cover. And also it has exactly 3 neighbors, A, B, C. And what we have here is 2 scenarios. That is, either the algorithm selects the vertex v to the cover. So in this case, the parameter decreases by 1 because S without v is also a cover of G without v. And the other option is that the neighbors of v are chosen to the cover. The algorithm chooses the neighbors. And in this case, what I claim is that the parameter also decreases by 1. And the reason is that if we remove all the neighbors of v, we also remove all the edges adjacent to v. So at this point, the vertex v does not cover any more edges in the graph. So if it was in a cover, we can just remove it from it, and we will still have a cover. And we can use this intuition to define a variant of our algorithm. It will have the same structure. We will look for a vertex v with degree at least 3, and if there isn't such vertex, we know that the maximum degree is 2, and we can find an optimal cover. But here, what we do with the vertex v will be a bit different. If the vertex is with degree exactly 3, we can add it to the cover with probability gamma 3, and add its neighbors to the cover with probability 1 minus gamma 3. And if it has at least 4 neighbors, that is the other option, we will add the vertex v to the cover with probability gamma 4, and we will add the neighbors, 4 of the neighbors of v to the cover with probability 1 minus gamma 4. So it's a slightly more complicated algorithm, but it still do one of the 2 options. It either selects v to the cover or its neighbors. We only played with the probabilities in some sense. And what I claim is that the success probability of this algorithm is now dominated by this recurrence. And let's take a look at it. So the first term here deals with the case that the vertex v is in an optimal cover, and it has the exact degree of exactly 3. So in this case, the algorithm selects v to the cover with probability gamma 3. And in this case, we reduce the budget by 1 and also the parameter by 1 because we added the vertex, and it's in an optimal solution. With probability 1 minus gamma 3, we add the neighbors of v to the cover. So we reduce the budget by 3 because we added 3 vertices, but we also reduce the parameter by 1 because the argument we said before, when we select the neighbors of v, the parameter also reduces by 1. The second expression, the second term, deals with the case that the vertex v is not in an optimal cover and has degree of exactly 3. And the same logic goes here with probability gamma 3. We select v to the cover. It's not in an optimal cover, so the budget decreases by 1, and the parameter does not decrease. And with probability 1 minus gamma 3, we select the neighbors of v to the cover. The budget decreases by 3, and because v is not in an optimal cover, its neighbors are, so that the parameter also decreases by 3. And the next 2 lines are just the same analysis for the case that V has degree 4 or more. And we have the same initial condition. And what we can do is we can use the main theorem to do the following: to find the optimal values of gamma 3 and gamma 4, and then to evaluate the asymptotic behavior of the recurrence. And what we get is that P of 1.5 k and k is roughly 1.035 to the power of minus k. So if we repeat the algorithm for the inverse of this P of alpha k and k times, we get 1.5 approximation with constant probability, and our running time is roughly 1.035 to the power of k, which is a nice improvement over the previous result. And this can be generalized, and you can reach nearly the optimal result we have in the paper just by adding gamma 5, 6, and so on. And the nice idea here is that usually branching algorithms are only concerned about what happens if they choose the correct option in some sense. They only focus on one path. And here it also makes sense to consider what happens if you go on a different path within the branching tree. Okay, so a short summary. What we have in paper is analysis of two-variable recurrence relation. We've seen the result. We didn't see the analysis itself here. It uses the method of types. We get a simple formula to evaluate the asymptotics. And this formula also provides some insights for understanding the behavior of the recurrences. And we use this analysis along with the idea of branching, or of randomized branching, to obtain faster parameterized approximation algorithms for vertex cover and 3 set. And we obtain significant improvements over the running time of previous results. And the algorithms are simple. And that's it. Thank you.
Okay, so let's thank the speaker. You can clap whatever way you know. Okay, any questions? I mean, we had lots of questions during the talk, but
I have a question. So what did you think quite general? So why don't you get any result for set cover with frequency f, right? Because vertex cover is just set cover with frequency 2. I assume that 3 heating set is just heating set and set cover are the same. So just I assume you mean like set cover with a frequency of 3, right? Why don't you get any result for any frequency? It just looks like it just changes the constant in the recursive formula.
So the reason I did, so there are two things you need to think about. First of all, what I've seen so far is that it's often very easy to take a problem and to apply randomized branching for it, and you will get some result. And it will be some nice result, but it will be very naive and trivial. If you want to get a good result, you need to understand the problem and then to provide some sophisticated randomized branching. That's the difference between the initial algorithm we've seen, which used the branching over 2 options, to the algorithm with branches over V and the neighbors. So if you want to have some result which is interesting, you need to understand the problem, and it simply takes time. That's the only limit I have. So I just didn't get to do it. I think the recurrence is general, and the idea is general, so you can find further applications. We have some initial ideas for feedback vertex set, but I won't be surprised that if you will generalize vertex cover to other directions, it will work there as well. Maybe you will need to do some adjustment with the recurrence and something, but the idea should work. I just didn't have the time to do it. That's all.
So I have another question.
Go ahead.
So I'm perfectly happy with randomized algorithms, but still I'm going to ask if you've thought about de-randomizing, more because I find the techniques interesting.
So the general thing that comes into mind is color coding, and I will have the same answer I had to Ray. I think it can be done. I don't know how to do it. And I think it's a very important question, because if you want the algorithms to be implemented, you don't mind about whether it's randomized or not in some sense. You maybe even prefer them to be randomized as they are. If you look for theory, it's a main drawback of these algorithms, and thinking it's an interesting question about how to overcome it. And the issue there is that the analysis of the algorithm involves significant dependencies. So I don't expect it to be trivial. I don't think you can take a black box solution and apply the distance randomization technique without doing anything. But
That's
I don't know how.
Interesting.
Yes.
I mean, there is this semi-generic approach of using Nissan's PRGs. Have you looked into it? It's like from stock 2001, Srinivasan.
I will ask you to send the name of the paper to me.
Sure.
The answer of whether I looked into it is no, I didn't have time to look into the randomization of this paper. Actually, my next step, it's goes by curiosity. My next step is to generalize the recurrences because I don't know, I liked it to a wider family. We can have recurrences which involve multiple functions and things like that. But it's not necessarily the right direction to progress with.
Yes, Rajit, you had a question?
No, I had this question about heuristics because he mentioned saying that when you do branching, so like in the first case, you actually taken the probabilities to be half and half.
Yes.
And later you actually mentioned that like in practice, these things work better. So probably like, heuristics come in terms of like selecting these parameters as well, because what you're doing is the worst case analysis in some sense.
So I'm not good about heuristics, so we should start with that. I know how to provide a worst case analysis. I think it can be done. Essentially, we optimize the parameters. So in some sense, the parameters are properly set for the worst case analysis. If you have some intuitions that the worst case analysis does not represent your real life instances, it makes sense to play with it.
Yeah. Thanks.
Okay, any more questions?
I'm sending
in the chat.
Yeah.
I will have it. Thank you.
Okay, any more questions? Okay, so if not, so let's thank Ariel again.
Thank you.
Thank you very much for listening.
I hope to see you.